Hello, can you hear me this time?
Yes.
All right,
Hi,
great.
Chad.
Hi, Leslie. How are you?
Good, thanks. How you doing?
I'm all right. I'm all right. Give me 1 second.
Oh, sure. You got to get your, yeah.
Well, I have a whole setup here in the back that I was planning to use, but my streaming computer just decided, nah, not today. We're just, so while it's restarting, I'm gonna just, I'll just present from my desktop.
Okay. Well, we generally start at 5 after. I mean, we're pretty flexible, so do whatever is most comfortable for you.
Nah, it's I'll save the fancy projection for later. If you can hear me well, this is fine. It won't affect the quality of the things I say, hopefully.
Awesome. But we still have to wait till 5 after. It's like an MIT. I mean, the MIT has this thing, right? When you say something starts at 2, it really means 2:05, or 3 means 3:05. That's just.
Yeah, for a long time we had Michigan time, which was 10 minutes after the hour. But the provost decided, nah, let's not do that anymore. Let's actually be on. Let's make real Michigan time real time.
Oh wow! Okay, yeah.
Which is less fun, I have to say.
You can play little mind games when 10 really means 10:10 and stuff. Yes.
Yeah. All right, I'm just gonna get set up here real quick.
Yeah.
And
in Spain, people show up late to gatherings, like pretty late, like half hour, 1 hour, 1 hour and a half, and there's no standard, so it's like a mess.
But if you announce a seminar in Spain for like 10 a.m., it's at 10 a.m.
Yes. At seminar, you have to be here. It's only parties between friends that it's a big mess.
Yeah, well, that's true here too.
Yeah, in the US, it's half that problem, I guess.
All right, I have to jump out real quick.
Okay.
I'll be right back.
We'll be here.
What did they do at Brown, Leslie? Do they have any sort of time adjustment or?
No, I think we started on the hour at Brown. I think it was on the hour. Harvard is 10 after. Harvard is like Michigan was, I guess. I don't know. Because I showed up there at Harvard one time to give a guest lecture, or Barbara Gross was out of town or something, and I was supposed to teach a lecture in her class, and she said 10, and I showed up at 10, and there was like no one, and I thought I was in the wrong place.
But then classes end before the hour because you cannot jump between.
Yeah, they would end. There was still a 10-minute. I think for everyone, there's still a 10-minute gap. It's just a question of where you slide it in the hour. So yeah. How's your computer doing?
I think I'm technology may cooperate. Who knows? I'm hopeful. But yeah. So I think whenever you're ready, I'm ready.
We'll start in 1 minute, maybe 1 minute.
All right.
Maybe you can start putting up your slides.
Will do. Could you give me? I'll do screen share this time. Could you give me screen share?
Oh yeah. Sorry. I made you co-host the first time you joined, but I forgot to do it now. Okay, you should be able to do it now.
Yay.
Here we go. You should see just white.
Yeah. Okay, so let's start the seminar now. Today we have Professor Chad Jenkins from Michigan. He's a professor there doing computer science engineering, and he's the associate director of the Robotic Institute. Professor Jenkins earned his bachelor's of computer science and mathematics at Alma College, and then a master's in computer science at Georgia Tech, and finally a PhD in computer science in the University of Southern California in 2003. He then served as a faculty at Brown University in computer science from 2004 to 2015. His research addresses problems in interactive robotics and human-robot interaction, and primarily focused on mobile manipulation, robot perception, and robot learning from demonstration. His research often interacts topics with computer vision, machine learning, and computer animation. Professor Jenkins has been recognized as a Sloan Research Fellow and is a recipient of the Presidential Early Career Award for Scientists and Engineers. His work has also been supported by the ONR, NSF, and the Air Force Office of Scientific Research. He's a fellow of the American Association for the Advancement of Science, a senior member of the ACM and IEEE, and is currently serving as the editor-in-chief of the ACM Transactions on Human-Robot Interaction. Welcome to the seminar.
Thank you so much, Farron, and I really appreciate people taking time to listen to the things I have to say. I've got a lot on my mind, so I'm just going to jump right into it because I don't want to go over time. And so I'll just start off by showing me. So this is me from a few years ago, and I would just, I've been in computer science and robotics and AI for several years, more years than I'd like to count, but when I'm walking around campus, if you went over my career and you asked and you thought about what people ask me the most, I would just put this to everybody and just ask, what question do you think I get the most when I'm walking around campus? And you can feel free to put it in the chat or just maybe a quick unmute or anything like that. Anybody? This isn't a quiz. It's not graded at all. So any guesses? What question do I get the most? I'll let you. What's that?
No idea. I'm working on it, but I.
All right. I'll break the suspense. The question I get asked the most is, "Oh, John, you want to?"
The robot's going to take our jobs.
Robots are going. You know what? I would love to say that would be the question I get. It's actually up here. It's actually am I with the football team? At some point they figure, it'll get to the point that I'm a roboticist and we may answer those questions, but usually it's sort of like football related, and I say no, I'm not with the football team. And one thing I would say is, have you seen how big those guys are? So I'm not a small guy, but I'm not a huge guy. And so one thing I did when I was in graduate school is to take my mind off of research, because you need something to get away. So I played rugby, and so that's a picture of me and the rest of the players on the team. I get to stand in the back row, but I'm not the biggest guy in the back row. So and so I get asked many more questions. I'm in my mid 40s now. I don't get this one asked as much. But it still happens, and that is when will I graduate? Sometimes I get that, so I try to leave a little bit of scruff on my face, so I don't get that one as much. And I say no, I'm actually faculty in computer science, and what I do is I program autonomous robots. I don't necessarily build robots the same way that people don't, that computer scientists don't oftentimes build their own computers and program to do things. We buy one. I program autonomous robots in a similar way. And so this is an example of the kind of robots that I've worked with. This is the Willow Garage PR2, probably familiar to many people on this call. But that was back at Brown when I was at Brown University, and so we'd had one of those, and it could move around, it could pick up things, it had an array of sensors, and so this was really sort of like one of the first mobile manipulation systems that we could buy. And we did a lot of outreach, a lot of trying to engage kids and youth and try to say that this is a job that you can do, but they still don't realize that. And so they ask, is this a real job? And I say, yes, this is something that a lot of people can be involved with. And increasingly as robots are becoming more, proliferate across our society, we need more people to do this job. But then that opens up a wide variety of questions that students might ask, or students do ask. Will robots take my job, John? That was it. Are you making R2D2? Can your robot buy me a drink? All sorts of things. And this time of year, I get a lot of, can I work in your lab? So like probably many of you are seeing. But in this talk, I'd like to focus on 3 of these questions. And that is, when will robots take over the world? So where is my robot? And can your robot bring me a drink? And let me start with the first one, and that is will robots take over the world? You're probably getting those questions as well, and And I can pretty safely say, at least not in my lifetime, robots are not nearly that smart. We're working on it, but I think by the time my kids are at the end of their career, maybe that might be a possibility. I don't think so. And part of the reason why I don't think so as well is that we program robots. We can tell them what to do, and we could have robots that help humanity as sort of one of our principal things we want them to do. And so one example I would give of this is work I did with Henry Evans, and so this was a TED talk that we gave a while back, and so we went on stage, and Henry from his bed in California was driving robots all on the stage in Washington D.C. and we're just and telling his story, and so he's best at telling his own story, but just sort of some highlights is that Henry is at the time, around the time he turned 40, he lost the ability to move his body, except for his head and a little bit of movement around his thumb. And so he relies on others to basically do his activities of daily living, eating, hygiene, just things like scratching an itch. These are things that he relies on others to do. Building on some of the web-based protocols that we were making at Brown for robotics, Charlie Kemp at Georgia Tech picked up some of these ideas and used them to create interfaces so that Henry could start to control robots on his own. And that gives him an avenue to basically do things physically so he could be independent. Moving towards that. It's still very much a dream. But imagine if you couldn't scratch an itch, and you have to scratch an itch maybe a couple times an hour or something like that. Imagine if you had to rely on somebody to do that and you couldn't do it on your own. This is maybe we could have robots do that. So this is as Henry recalled, this is the first time Henry was able to shave himself. At that point, I think in over 10 years. So being able to the vision of being able to restore independence to somebody who had lost physical independence is something that's really, it was one of the things that moved me a lot about, and remains sort of a highlight of our career, of my career. And so a lot of what was underneath this was something called Robot Web Tools, and so Robot Web Tools is based off of underneath all of it is trying to enable TCP/IP like interoperability for robotics. This is centered around the Ross Bridge client-server messaging protocol, and so the idea is that we don't really care, if you're a user of ROS or LCM or something like that, you get embedded into the build system and all the things to make it compile and run. But but for making all our systems work together, all you want to do is just speak the right protocol over the wire, and that's what allows for the great things we can do with the internet today. And so Rossbridge, along with client libraries and visualization libraries, has allowed us to make all sorts of interfaces to a wide variety of a wide diversity of systems, but most importantly, create web interfaces for various types of needs and situations. And so one of those came about when Henry was like, I want to fly drones. And so some of my colleagues at the old Willow Garage said, Henry wants to fly some drones. Can you help him out? And so I'm like, sure. And so I went to the Palo Alto Mall and I bought an AR drone, and I made this in the space of like an afternoon. I made this little interface that allows you to just from just using sort of mouse clicks, being able to move around and fly the drone around. And I made sure to make the buttons really big, because when you have very coarse control over a cursor, as Henry does because he can use his glasses to track the cursor movement and just basic movement of his thumb to be able to press the button. We had to make this very accessible for him, and so we did that. And then I took it up to his house. And so you can see the drone. This is Henry in his house, and the drone is outside, circled in red right there. And this was his first flight, and it was just, and he was really excited about it. Just being able to move around and just experience the world in ways that you can't when your physical mobility is restricted. You know, the first thing he wanted to do, I'm gonna turn that down a little bit. The first thing he wanted to do was wanted to go fly into his garden and see how things were growing. They had solar panels that they had put on his roof, and he'd never been able to see those solar panels, and so he was able to go up there and check that out. He wanted to slam dunk a basketball, but I told him we couldn't put a basketball on this thing. It was way too heavy. But you know, at least he got to land on his basketball hoop. And so this was just, I would say, one of the things that you can do when we have this type of accessibility, this type of interoperability for robotic systems. And so Robot Web Tools is out. It's you know, Rossbridge is in pretty significant use. You know, this is just a sampling of the things that people have done to interfaces and that people have made with Rossbridge, but it's something that, you know, and there's a lot more. I actually made this slide about 2.5 years ago. And so there is much more that's out there. And I'm always amazed to see what people do with this and the types of things they could imagine. And when I show this to people, when I show this to people that come into our lab, that usually makes students and other people say, that sounds cool or awesome, or it's really inspiring, or they bring up, it's like some show that they saw, like Silicon Valley on HBO, right? And so you know, this really gets people talking. But eventually the conversation comes towards the next question, which is, so where's my robot? We've done all of these things. We have all this capability. You're getting all of this opportunity to help shape our future with robotics. Where are your robots? Where are the robots that should be in people's lives? And I say that, you know, those robots are here. We have drones. You can go buy one. Autonomous cars are coming. You're increasingly being able to get to see those on the road. We have robots in factories. We have robot vacuum cleaners. But when people ask, so where's my robot? What they're really asking for are human scale mobile manipulators, like the PR2, and you know, and like the fetch system here. This is the fetch robot here to the left is the first my first purchase when I came to the University of Michigan. And you know, and so this is really what people are looking for. They're thinking about Rosie the robot from the Jetsons or other types of robots from science fiction. But really, it's more like they want robots that could be human partners that can work with you in just like another person would, or in a similar way. This leads to a question I would have for you. You know, so some people probably know the answer to this, but how much do you think these robots cost? How much do you think it would cost to buy one of these? And so usually I would say you can put that in the chat or unmute or something like that. Just think of it like The Price is Right. If you watch that show, I watched a lot of it as a kid. Try to get as close as possible without going over. Any guesses?
You need a guess from someone who hasn't written a check for one.
Yeah, I know, right? Exactly. 100K. Thank you, John. Thank you. All right, I won't keep you in too much suspense. 100K. I like that. I'm going to go with that because if I plotted this out over time, 100K is exactly what I paid for my fetch, and so I bought that robot in 2015. The Willow Garage PR2 came out in 2009. I bought mine in around 2011, about $400,000. If we think about this if I think about this with respect to the first robot that I started working with, it was the NASA Robonaut down in Johnson Space Center. And you know, you can't get an exact number from NASA on this, but I don't think anybody would balk at $1.5 million for that robot. And so if we remember how to do our least squares fit of your favorite order polynomial, you know, we can see what the trend line looks like in this case. And you know, and so I would make the argument that your robot is actually here. It's in 2020. And I made this slide a few years ago and I said your robot will be here in 2020, about $40,000. And so so if you're looking at platforms like Hello Robot or some of those some of the platforms that have come out, you know, sort of around the $15,000 to $45,000 range. We're starting to see mobile manipulators come out at this scale. I would also say that the economies of scale is going to drive this cost down considerably. The NASA Robonaut, they made, I think, 3 to 5 of these platforms, some on the International Space Station, and they cost a lot of money because they were custom. The PR2 got that down. I believe they made about 60 of the PR2s for $400,000 each. The Fetch now is, I'm assuming that they have a couple hundred units, several hundred units out there, and it got down to 100,000. So the next generation will probably be made, at the thousands, depending if we can create the right applications for these robots to create the right demand. But this only talks about the platform itself, the hardware. If we think about how you control these robots, you can see sort of generations of different types of control that has happened. So if we look back when I was a graduate student and using things like using platforms like the NASA Robonaut, everything was mostly remote control, just straight teleop. So you would have, if you really want to get something done. And so that meant that that you had to really exchange your body for the robot's body, and then you're just teleoperating it and doing and you're using its body to accomplish a task. But with the rise of RGBD sensing and laser rangefinders, we've been able to localize and map and plan such that we can do what I would call put their tasks. I can pick some object up at location A and drop it off to location B. And so I can do that we do that often with our mobile manipulation platforms, but really that's what autonomous driving is doing. Your car comes to pick you up at location A and plans a route and follows that route to drop you off at location B. I would argue what we're trying to do in the next generation is to have robots do a task for you. And so that means that the robot is you're trying to say, you're trying to give it some higher level directive, clean my room, make me breakfast, assemble this structure, put the birdhouse together for me, fix this structure, fix my car. And the robot should be able to reason through all the steps and all the motions in order to affect that desired change on the world. And so this next stage is really not just do this task for me, but it's really about how we can make your world programmable. The same way that computing technology had made information programmable and automatable, and virtual worlds programmable, we would like to do that for the physical world. The challenge is that our world is complex, and even just something as simple as your kitchen. You can have hundreds or thousands of different types of objects that are in your environment, and we can see some of those. We're increasingly getting better at seeing more and more of these items, but a lot of traditionally our robots have been blind to most of the objects that are here. And even if you can see that object, you still have to know its form and function, about how you should use that object, the semantics around how to use a bowl, or how to use or how to open a drawer, open a refrigerator, use the cutting the cutting board, or pouring something out of a mug. That coffee maker that's there. We, as roboticists, we are infatuated with coffee makers, and so we still have a long way to go. But what I would say that we're trying to do, what at least is guiding my group, is that we're trying to make computational systems such that we can make them taskable. That means that we could have computing such that we can take an arbitrary robot, show it an arbitrary task, and have it perform in an arbitrary environment. That is really what we're striving towards. Traditionally, this has been the goal of robot learning from demonstration. And this area has been around for a long time. There's lots of people who have been doing it. But if we could just show the robot what we want it to do, then and it could understand our intention or mimic our motions, then it should be able to carry out this task as well. Part of the reason why I'm especially glad to speak to MIT today is from my understanding, or at least my literature review, learning from demonstration goes back to the copy demo, the AI Lab copy demo from back in the 70s. So this is Patrick Winston, who's sort of the earliest earliest person who I could recall doing something like this.
Is that really Patrick? Wow, that is amazing.
That is, yeah. It's you can go to this URL right there, and that is him. Yeah, had to do a lot of literature review to find it, but it's there.
It was actually a bunch of people. Patrick was one of them. Bertolt Horn also played a big part on the actual robotics part.
Right. Eugene, I'm currently on I'm doing activities with Eugene Freuder, and so I believe he's involved in this too. And so just a lot of names that we've come to recognize are here. But the idea with this is that you would be able to just demonstrate a scene to a robot, just sort of say, hey, this is what I want to have happen. This is what it should look like. You would perceive that scene and say, the robot would say, all right, this is how it's structured and what needs to be accomplished. And then the robot would be able to see that, to take those materials and then be able to reproduce that scene. And so this is the origins of this. Is from my understanding, this is the origins of learning from demonstration. If we take those ideas and we sort of situate that from, what if you don't care about learning from demonstration? There's all sorts of other approaches that you could take. And when we're thinking of, and so my colleague John Laird and I wrote John did most of the work, but wrote sort of a survey that sort of said, well, what if you don't really care about learning from demonstration? You want to just think about the best way to get something done. And you could lay out possible approaches with respect to task performance on the vertical, scalability of the new tasks on the horizontal, and the ease at which you can specify what the types of programs you want for a wide variety of users. And you can use this 3D space to lay out possibilities, sort of with your traditional programming language being, probably the most performant way of doing this, at least for now, but difficult to scale the new task without recompiling and not necessarily easy for people to do. And so learning from demonstration has its sort of place here. But what we're trying to do is change this a bit. And so if we think about what learning from demonstration is now, but what it could be in the future, sort of the next generation of learning from demonstration, what we're trying to do is sort of move it out further along. I can't say much about the ease of interaction given my skill set, but I think we can make these systems more performant and more scalable. And this really is trying to think about how we can produce goal-directed robot behavior from workspace demonstrations, similar to what the copy demo did. And so I think what we're seeing is two bodies of literature that could be coming together. Semantic mapping for 3D perception of space, and the semantics involving various objects. I'm not supposed to use the word affordance, but I'm going to say the word affordance. The semantics of affordance for these objects. And then combine that with planning-based programming, declarative approaches to programming robots. And so if we bring these together, I sort of call this in my lab, what we call this is semantic robot programming. And so we can be able to work with common objects and just be able to go up to a robot and show, hey, this is what I want the world to look like. Then have the robot be able to perceive that scene. I don't fully trust neural networks, but we use them. We use them on the front end, and then we combine that with probabilistic inference on the back end, usually particle filter or non-parametric belief propagation. And then we use this to infer the scene graph stored in the planning domain description language. If we can do that, then we can represent what we want this goal to look like. And then if the world looks different in the future, we can also perceive that world as well. That's the state of that world, store that axiomatically as PDDL. And then once we have that, we have a representation both for the current state of our world and the goal state, such that we can reason over all of the actions that are needed and the motions in order to realize the goal state from the current state. And so what we're showing here is just for the example is just realization of that of the goal state, working through this problem on its own. We did not, other than just showing the robot the goal, we didn't tell this robot anything. I mean, we turned it on and we ran SSH and got everything running, but it's doing the reasoning all by itself. And that's really, I think, where we're trying to go. There are some limitations to this. In this case, we're just showing, and so this is just showing that that we got a copy of the goal. It's not perfect. It's not a metric reproduction, but in terms of the relationships of the objects, it's correct. And we ran this a bunch of times. But while that's just sort of going, and so the goal is in the upper left-hand corner here, and then you're seeing the robot try to realize that goal. But there are some limitations to this, and that we are we're showing a specific goal in this case. What happens when we show multiple demonstrations, and we want the robot to start to learn a more generalized notion of our intent, a more generalized notion of what we're trying to accomplish, and being able to distill that from multiple examples is something that is an ongoing effort of our lab. But in general, how do we start to understand what you want? If we can understand what you want, then the robot can figure out how to do it. And I think that's where learning from demonstration is going to go. In order to accomplish this, there are some problems. Perception does not come for free these days. And so scene estimation and clutter is actually a pretty significant problem. We need to estimate the 6th degree of freedom pose, position, and orientation for all these objects, as well as the relationships between these objects. What's stacked on what is physically resting on other objects. It may be verboten today in robotics to assume object geometries, but I would make the case that we still need object geometries. But but maybe neural networks can do more for us. And the reason why we do this is so we can address all sorts of uncertainty that's due to physical interaction, occlusion, stacking, off-balance contacts, multiple supports between for given objects, and so we have to deal with all of these. I'd like to be able to start to do this without the crutches that we typically rely on in robotics. No green screens, no shirt-loose style monocular colored objects. We don't have to have singulated, isolated objects. And AR tags are great. I'm a big believer in Ed Olson's April tags, but we shouldn't have to rely on those. And what gives me a lot
motion capture? How about motion capture systems?
Oh, that's the absolute worst. That's like now you have to have like 10 cameras with the little reflective balls on it. That's funny. What gives me a lot of hope is what I've seen from autonomous driving. Which is fabulous. It's the most non-motion capture thing you need in order to make things work. And so some of my colleagues here at Michigan and alums of MIT have produced fabulous work in terms of autonomous driving and being able to build geometries, being able to perceive at the city scale. And so Ryan Eustace and his group and at Olson, they would drive they have laser rangefinder on the top of their car. This is work they did with Ford, and they would be able to build fabulous maps of 3D space. So this is downtown Ann Arbor. That was the football stadium before. And so what you're seeing in blue is what the robot mapped out previously, and what's in red is what the robot is seeing now from its laser rangefinders. And so we can get 3D occupancy really pretty well. I would leave it to people like John to say more about that than I would know. But I can say what we're missing are the semantics. Do we know for particular points that that's a car next to us? Those are bicyclists going through the intersection. That there's a tree, or those are buildings, and we want to treat each of those objects differently based off of what we know about their semantics. And so in order to address this problem, I take a lot of inspiration from how we do goal-directed navigation. We have some robot in our environment. We do localization probabilistically, usually through some form of Monte Carlo localization. And then we take an estimate off of that, and then we can do something more deterministic. We could do A-star path planning, for instance, to then get our robot to navigate to a goal location. And so there's this synergy between probabilistic inference and symbolic deterministic inference. If we apply this to mobile manipulation as well, we can see we could see how this could lay out as well, in that if we can estimate the scene and then be able to take an estimate, maintain belief over those possibilities given the uncertainty from perception, from partial observations, then we can take that estimate and then do planning off of that, and then continue to this loop over and over. And even if we're wrong in terms of what our estimate is, we have probability mass in those other locations to correct based off of actions that are taken and what we see in the future. And so this really, the scene estimation part, we've got reasonable answers for most of these. I would say reasonable but not perfect. The scene estimation part is something we're just starting to see get traction in robotics. And so one of the pieces of work that we've done in this regard is sequential scene understanding and manipulation. And so the idea with this is that we just dump objects onto a table, and the robot should be able to recognize objects and put them into the appropriate bin. So either laundry objects that go in the laundry room on one side, and objects that don't go in the laundry room on the other side. We localize their 6 degree of freedom pose so that we can put them, so that we can perform the grasp and put them in the right location. You should note that the Comet doesn't go in the laundry room, that goes in the kitchen for dishes. I don't think my students do a lot of dishes or laundry, so that's their mistake, not the robots. But the idea is that we need to recognize and be able to get poses from objects in these cluttered situations. The way we do it, our general approach is that we use neural networks to give, and this is RCNN in this case, to get an estimate of to get an idea of what's out there as sort of to refine our search space. And then what we have on the back end is we use probabilistic inference to give an idea, to then sort of, usually as a particle filter or non-parametric belief propagation, to just sort of search through those options, given that we have a known model for RGBD data that we're looking to match against. And so this is something that just runs on board of our robots. For the sake of time, I'm gonna skip the rest of that video. All of our videos are online. You're more than welcome to take a look. But this gets to some of the challenges that we have for making semantic robot programming work. Our search space for all types of cluttered scenes is going to be quite big, and it's going to grow exponentially with the number of objects. And so we're looking at ways of doing efficient non-parametric belief propagation as a way to do probabilistic inference in space. And when I say efficient, it's really, we have a lot of models and a lot of algorithms right now, but how do we think about the systems aspect of doing that inference? The same way that GPUs have and currently it has enhanced our ability to do inference with neural networks. I think a similar renaissance is available for probabilistic inference. Our world is dominated by translucent and transparent objects. And so we've looked at things like planoptic cameras, other types of sensing in order to deal with these types of objects, representing affordances. And our paper from ICRA this year was about going beyond the tabletop. So a lot of times our manipulation sits on some sort of tabletop. Can we start to extend this to the building scale and be able to maintain object permanence belief over larger areas, even if these objects are not currently in the view of the robot. And so with this, in this case, we're picking up a wine glass, or I guess I'm not supposed to call it wine glass. We're picking up some sort of beverage container, and so this usually starts to get people to ask, "Can your robot bring me a drink?" And the answer is sure. We can do that all the time, except if you're a roboticist. Oftentimes, drink means beer. I've learned that over several ICRAs, and so sure, we can do that. No problem at all. We've done that multiple times, and so so this is just sort of a common thing that we have robots do. And usually when we do that, this is especially when you get the references to popular culture. And have you seen this on that show? This looks like that robot that did that thing. And the one that gets me the most is this seems like what I saw on Silicon Valley on HBO, and that one hits me a lot, because in that show, they're always saying that they're making the world a better place. Whatever they're doing, whatever startup or company or whatever they're working on, it's making the world a better place. And so they've had a number of these, such as we are making the world a better place through constructing elegant hierarchies for maximal code reuse and extensibility. Okay. This one caught me by surprise. We're making the world a better place through scalable, fault-tolerant, distributed databases with ACID transactions. All right. The one though that absolutely got me was from the CEO of a fictional big technology company, naming no names here, that was called Hooli. Which I actually learned in giving this talk that Hooli actually means something not nice in Russian. So learning something new every day. But the CEO of Hooli said that Hooli is about making the world a better place through minimal message-oriented transport layers. And I was like, whoa, like really? Because what got me is that if you replace Hooli with Rossbridge, which is the robot messaging protocol I talked about earlier, then that's me. Then that's really me in that spot, right? Am I really, is this just a lot of talk that I'm doing, or am I actually making the world a better place? This keeps me up at night. I love what we do on artificial intelligence and robotics. I find this fascinating, but I'm always asking myself, are we actually doing right, such that our what we produce will actually make the world a better place? It's a big question. And when we look at the world, a lot of people had some soul searching that we had to do as a society that came from Memorial Day this year. And so we all saw we're shocked and horrified by what happened to George Floyd. I can't hold my breath for 2 minutes, let alone try to do it for nearly 9 minutes. And it really, I think people understood that we have some big issues we have to deal with in our society. This led me and a number of people and a number of Black computer scientists and our allies to be able to create an open letter and call to action. And so you can look at that at blackincomputing.org. And so this gives some thoughts about what we can do as individuals, as communities, and as organizations to try to help address the issues of systemic inequality in our field. But this still was rather nebulous. It was sort of high-minded, and these are principles, but it didn't really come home until later in the summer when we learned about what happened on the evening of January 9th, 2020. On this occasion, it became very real for computing and AI, because that is when Robert Williams, on that evening, when he was falsely arrested, purely off of an incorrect facial recognition hit. A neural network got a false positive, and because of that, Robert Williams was arrested by Detroit police, not far from Ann Arbor, where I am now, in Farmington Hills, Michigan, and was arrested in front of his neighbors and his family, and was detained for 30 hours. And I don't even want to think about what he had to do to get his record cleaned up. So what they did was just basically took this blurry blurry surveillance camera data and matched it to him, and that was it. And so I would ask people to look at the story. I can't tell the story for Robert Williams and his family. You should hear what they have to say. And so they've given their account online. There's also the ACLU report on what happened as well, and Robert Williams' op-ed in the Washington Post, which gives some insights into not just what happened to him, but what we should be thinking about as we're developing these technologies, what our field should be thinking about. And so this really is a big issue, in that this is the investigative lead that happened. Blurry picture to suspect. And we've seen that over the summer. We also saw that you could take blurry images of gradient blurry images, and we try to do super resolution with that. If you don't do your training the right way, or you don't do it in a fair way, you would get you can get very incorrect results, such as matching President Obama to somebody who is not President Obama. I'm going to skip this bit about everything that goes around this, and just say we got to think about the cultural context that's happening. But I would say that something that we should consider is that, you know, deep learning has taken off in our field of robotics. If we look at what, you know, the amount of papers, the amount of intellectual attention we've given to it, it has shot well beyond your standard your standard areas of that get the most sort of intellectual mass. Task and motion planning, localization, SLAM, multi-robot systems. Deep learning is far and away getting more attention than that, and so we have to be really careful about what we're doing when we're developing this research. I would argue that so earlier in the summer, I basically apologized to Robert Williams because I said, you know, AI is we've just failed systemically. And so this really is, the issue is that we've just had not people that represent his viewpoint in AI research. And so this is, you know, we haven't had a lot of people in the research process as AI has developed. Because research not just is in the research lab and those ideas, but also the people we teach in the classrooms, we have low production of Blacks with CS degrees, and that leads to how people think on development teams, and those development teams then develop the systems that are produced for end use. And you know, and if there's not wisdom in the room, then it just doesn't happen. And so that leads to uneducated use of technology, not just by law enforcement, but across many different dimensions of society. I would defer to some of my great colleagues that work in algorithmic fairness and bias on what I would consider to be the front end problem. And so I'm just picking, you know, I'm just selecting fabulous work by Joy and Timnit here that from 2018, and I would encourage everybody to go read that paper about what we're doing in terms of using this technology. What I think we can do as academics and people at universities think about the back end problem. How do we address the issues in the classroom and in the research lab, and such that we can have better outcomes in terms of what it looks like in terms of the development teams and the executive boards. I would also say, I stole this picture from Viola Jones. I don't blame Viola Jones at all. This is not about one particular research or being able to look at this intellectual domain, and we shouldn't really be taking options off the table. This is really a systemic problem about how we incentivize and practice artificial intelligence. And if we look at the results of that, we've just failed to include Black people in the advances of artificial intelligence. A book that I love historically is The Quest for Artificial Intelligence by Nils Nilsson. You know, I didn't buy it. I need to go buy the book, but I've read his PDF, the PDF on his webpage, several times, or you know, as much as I can read something that doesn't have a budget or an equation in it. But it is a fabulous way to hear about the origins of the field, how it's come up, who has invested in it, and the people that have made a difference in the field, and just the evolution of it. It's really fabulous. I love this book, but I also know that in name dropping, there are zero Black AI researchers cited. It basically is sort of saying that Black people have had no role in artificial intelligence, but we are going to be bound to its implications. If we look at Intel came out with numbers and basically said, you know, if you look at the population and the labor force as a whole, and then you look at the tech sector, we see vast disparities here. And this is what we're considering to be what's considered to be a disparate impact. It's not that people are barred from entering the field, but the field is doing something such that we're seeing inequitable outcomes. This is different than disparate treatment, which is the segregation that we've seen from the 50s and 60s. Coloreds only bathrooms and whites only bathrooms. That's disparate treatment. But disparate impact is when you're seeing similar effects, just not legislated as hard and fast rules. We know that the results of this disparate impact leads to bad outcomes in terms of what we produce in terms of software and other outputs that come from our field. And you know, this is really about, you know, I'm suggesting a lot of things that you should think about globally, but specifically, if you're going to think about what you can do, it's about what you should act locally in terms of being a better citizen through AI and robotics. And really, you should understand how the system, what drives the system. It's not just about, you know, various actions here or there, but understand the underlying motivation. and so I'm going to be a little snarky, but there's always going to be some a little bit of truth in the humor as well. And so if you think about the formula for succeeding in research, what you should do is create a bubble of competent looking people that exude success. If you can do that, you can get your proposals funded, and you can produce results that enhance your visibility and your profile. You use that to then form alliances to build networks of like-minded researchers. And then you sort of do some collusion to promote the views of the alliance, not forgetting to dismiss dissenting views, but with civility. And then you use that patronage to place your people in academia and industry, and then you use that to rinse, wash, repeat over and over and over, and then produce this cycle over and over again. This is a way to be successful, but it's not necessarily a way to be inclusive. We're seeing that this same model is that we have in research that has produced some of our bad systemic outcomes also applies to law enforcement, because a lot of what we read this summer about police unions is they use the same model in order to build these networks of like-minded people that produce the kinds of effects that we see with respect to George Floyd, Ahmaud Arbery, Breonna Taylor, and way too many others. And so this is something that we have to think about. I should underscore, this is not saying that we should defund the police. That is, we need law enforcement, absolutely, but we need a different outcome from law enforcement. We need them we can support them, but also hold them accountable, which is what we need for research as well. I would say that this is something we should also be thinking about. So I put this slide in here just for MIT. I would recommend looking at systemic inequality and hierarchy in faculty networks. It's a paper from AAAS. This gets to MIT more than any other school has a huge say over over the culture of our field. And so I would recommend just taking a look at this article. What can you do? I know I only have like a minute left or so I'm going to try and speed through the rest of these slides. I gave a talk a few years ago and just sort of said, there's some things that you can just look at. You can just ask yourself in terms of your double standards. Are you consistent in your treatment of colleagues, students, applicants, other people who are looking for an opportunity? When you're looking at your outcomes, you can see, are you diverse in your research lab, your citation list, your classroom, and the committees that you're on? One thing I forgot to say back in 2012 is, how diverse is your funding review meeting? Who is getting the investment in terms of the time and given the resources to be able to pursue what they think is right? And I think that one is really important in terms of the nation's investment. I'm going to skip a lot of these. Our curriculum needs an update. We're still working with some old models. I'm developing a robotics curriculum, undergraduate curriculum at Michigan. We're leading with linear algebra instead of calculus, because kids you're just pounding them with four semesters of calculus before doing some fun stuff in linear algebra. Let's do that first. And I'm gonna skip that. And we don't even have to pass new legislation in order to make this possible. The Civil Rights Act of 1964 basically says if you're getting federal money, you have to produce equitable outcomes, and you have to provide equal opportunity for employment. We've seen how this has been great. This has improved our field with the Title IX of 1972, which said that if you're going to provide any opportunity in higher education, that has to be balanced across sex and gender, on the basis of sex. And so I would say that Title IX allowed for my mentors to get an opportunity and then mentor me when I got a chance to be in our field. I'm going to skip this joke right here and just end by saying we need more empathy in our field. Our work has real consequences. This isn't just laboratory experiments that we're doing. We're seeing real effects. And so in that regard, when we're considering the innovation and excellence that we're trying to strive for, the things that stimulate us intellectually, we have to balance that against our need for our responsibility to create equal opportunity and produce the right outcomes, and make sure that this is balanced against our economic incentives, what drives us in terms of funding, what drives us in terms of the rewards that we want to get. And if we can balance these, we can be right at the intersection. And that is really where I think our field needs to be, and where society needs our field to be. With that, I thank you very much for your time.
Thank you.
Thanks for the great talk. If they have any questions, feel free to unmute yourself, or if anyone is talking, you can just raise your hand or write it on the chat.
Can I go? I thank you so much, Chad. I just am so supportive of your entire talk. You know, like the research side and the more societal impact side, and whatever I can do to help, I want to be an ally. I think in the research setting, my students are deeply interested in the sort of connecting like semantics and understanding, getting from the messy, uncertain perception to actually doing stuff in the world. And I do have a meta question. There might not be time for this, but I think about what it takes to get papers published in our fields and conferences, especially conferences more like CVPR, where there's a certain, the amount of evaluation that's expected to get papers in, and it tends us towards like yet another paper with the kitty data set with like a table with 20 different numbers and some are bold. And that to me seems almost like at odds with like having robots trying to do challenging end-to-end tasks that you're showing in your work. I think we need more of the latter, and we need sort of a way to how do you cover the sort of evaluation aspect of research for the more messy real world setting with a real robot doing real things, as opposed to sadly you can be a robotics student with never touching a robot just by being good at extracting kitty cityscapes, all the different data sets that are out there. What are your thoughts on that question?
I would say I really appreciate you saying that, and because it's a constant struggle with my students to get them not to just to go down the route of just doing evaluation with a cultivated data sets. I think a lot of them they would sort of veer into being computer vision researchers if I don't push them to do things with the robot. I worry that in terms of our peer review system and our merit review system, that we're sort of converging towards a local minimum because neural networks are so easy to use. We can train them up. You can get a result. You can produce that threshold unit of publishability really quickly, and so that seems like the way to do it. That students are incentivized to do that. But I think the real issues, the real interesting ideas require exploration. There is a balance. When we think of science is about reproducibility at the end. It's about, you should never trust anything that I say. You should only trust what you can do from what I've said. And with that, there is scientific exploration, which is trying new ideas and seeing what you can learn from them. And there's scientific rigor. We overemphasize rigor sometimes at the cost of exploration. And I think anybody in reinforcement learning can tell you can't overexploit and not explore.
Well said. And just briefly, I care deeply about faculty search. I'm very involved in it, and if I could ever talk to you offline about ways to expand search and to make we need more beacons for faculty careers, and that's why I applaud what you're doing with Black in Robotics. I was delighted to see that Ayanna Howard was announced as the Dean of Ohio State on Monday.
Yeah,
it's really wonderful, and we need to amplify our voice, our leading voices. And thank you for being such a voice.
I appreciate that, and I owe you an email, so it's on my list this semester.
I owe an email too about the Wilson Foundation. Anyway,
we will get that opportunity to talk. But thank you so much, John.
So Chad, thanks very much for the talk. That was great. And all aspects of it.
Thanks so much. I really appreciate you taking time to listen.
We really appreciate you taking time to talk. So good job.
Awesome.
Okay, so maybe we let people off the hook since it's a little over time.
Sounds good. Great talk.
Yeah. All right. Had to go. Thanks for taking the trip to Cambridge.
It's the easiest, but maybe not the best trip. So.
Yeah. Thanks, Ron, for organizing, and thanks, Chad, for great talk.
I'll create a few one-on-one meetings. So if you want to have a one-on-one with Chad, I'll send an email in the next few hours.
Okay. This is the only one good thing for this whole COVID pandemic thing, is that actually going to give a talk someplace else is now much easier. And, we've had people from South Africa talk in our group, in real time. And it would never have happened before now. But so maybe we should kind of keep that going into the future, because it really is better in some sense.
Yeah, when we started the seminar, I think we got like $2,000 in funding or something like that to bring researchers. I was like, okay, how am I going to use the money to bring researchers?
Well, so you mean
the started, I'm like, okay, now everything is
the pandemic just to stretch your budget?
What you could do is send people little gift boxes. Like if you come to the Zoom link, we'll send pizza to your house or something.
Oh, that is not an uninterested suggestion, I imagine. It's a good idea, though. Sending a little gift is a good idea. Yes.
Yeah, I wish I could do that for my students, but they're all over the place. I have a lot of students in class.
Yeah, no, I was teaching a large class last term, and I had people in 15 time zones.
Wow.
And the staff for the class was in 5 time zones.
Wow.
There was 600 students, and they were like literally all over the world. So that was a new experience too.
Yeah, but I think a lot of this, some of these ideas will stick with us, right? Because it is, I do worry a lot about the carbon footprint from from flying all over the place.
And your point about inclusiveness and reaching, I mean, there's been this enormous barrier for people accessing education. And, in principle, over the, we've had electronic access to materials and so on, which is not the same. But really over the last year, in some sense, some of the physical and technological barriers have dropped a little bit in terms of access to people and materials and so on. And that's actually probably a good thing if we can keep that going.
Absolutely. And do it. I think, we saw with MOOCs that there were, people thought MOOCs were just going to take over and just be the dominant idea. But what we found is that people still need connection locally. And so that right balance of distributing it, but still, distributing globally, but still feeling that connection locally. If we can do that I think would be that will mean a lot in terms of how we can revolutionize the way we do the academic enterprise.
Yeah, no, I think it's in principle doable. It's going to take will and to break down a lot of barriers. But okay, I do have to